Matter can exist in different states such as solid, liquid, gas, and plasma. In a solid, atoms are packed tightly together, preventing free movement. This compact arrangement makes solids retain their shape. In contrast, liquids have atoms that are close but not tightly packed. These atoms can slide past one another, allowing liquids to take the shape of their containers. Gases have atoms with enough energy to move freely, as the forces between them are too weak to hold them together. Plasma is similar to a gas, but it has the unique ability to conduct electricity. Physical properties are characteristics that define how a material behaves. Flexibility refers to a material's ability to bend without breaking. Density is the measure of mass in relation to volume, indicating how compact a material is. Electrical conductivity measures how well a material can conduct electricity, while hardness is about resistance to being scratched or dented. Thermal conductivity indicates a material's ability to transfer heat. Miscibility describes the ability to form a homogeneous solution when mixed, such as in liquids. Ductility and malleability are properties relating to shape of materials. Ductility is the ability to be stretched into a wire, whereas malleability allows a material to be flattened or shaped without breaking. Let's explore some important physical properties of materials. Elasticity refers to a material's ability to return to its original shape after being stretched or manipulated. Luster describes how well a material shines by reflecting light, while viscosity is the resistance of a liquid to flow. Next, we have melting and boiling points. The melting point is the temperature at which a solid turns into a liquid. Conversely, the boiling point is the temperature where a liquid turns into a gas. These properties are crucial in understanding material behaviors under temperature changes. Materials also possess magnetic ability, which measures how well an object can be magnetized. Brittleness is another property indicating how easily a material fractures under stress, showing how hard it can be without breaking. Solubility is the capacity of a substance to dissolve in another at a specific temperature and pressure. Turning to chemical properties, flammability is a material's ability to catch fire, and corrosivity refers to how a material can gradually degrade others through chemical reactions. Finally, we discuss acidity and basicity. Acidity is the ability of a substance to donate protons or accept electrons, while basicity is its ability to accept protons or release electrons. Physical changes affect only the physical properties, not the chemical composition of the material. In chemistry, different types of mixtures and solutions play important roles. A solvent is a substance that dissolves other substances like water. Meanwhile, a solute is the substance that gets dissolved, such as salt in water. There are different types of mixtures, such as suspensions and colloids. Suspensions have large particles that settle at the bottom, making them heterogeneous. Colloids, however, contain smaller particles and display the Tyndall effect, which is the scattering of light. Various techniques are used to separate mixtures based on their properties. Chromatography, for instance, separates mixtures by moving substances at different speeds through a material. Another method is decantation, which involves pouring the liquid off the top while leaving the solid sediment behind. Filtration is a common method that uses a filter to separate solids from liquids or gases, like straining pasta. Evaporation is another technique where heating a liquid turns it into a gas, leaving any dissolved solids behind. Distillation is a process where a liquid is heated to become a gas and then cooled back into a liquid. This technique is used to separate substances based on their boiling points. Understanding these processes is fundamental in studying the atomic structure and models proposed by scientists throughout history. The concept of the atom dates back to ancient Greece, with Democritus who coined the term atomos, meaning indivisible. He laid the groundwork for the notion that atoms are the fundamental building blocks of matter. Jumping forward to the 19th century, John Dalton characterized atoms similarly to billiard balls. A key figure in modern atomic theory, Dalton's ideas set the stage for further scientific exploration. In the early 20th century, J.J. Thomson introduced the plum pudding model. He proposed that atoms are composed of negatively charged electrons within a positively charged sphere, signaling the presence of subatomic particles. Ernest Rutherford's nuclear model changed our understanding of the atom structure. Through his gold foil experiment, he discovered the concentrated positive nucleus at the center, surrounded by electrons. In atomic structure, electrons carry negative charge, protons are positive, and neutrons are neutral. This knowledge forms the basis of today's atomic science. Atomic structure is defined by several key components: the atomic mass, atomic number, and elemental symbol. The atomic mass is the sum of protons and neutrons in an atom. The atomic number indicates the number of protons, which also equals the number of electrons in a neutral atom. An example is an oxygen atom, denoted as 1608. Here the atomic mass is 16, the atomic number is 8, which means it has 8 protons, 8 neutrons, and 8 electrons if neutral. This illustrates one type of atom structure where protons, neutrons, and electrons are balanced. In contrast, consider carbon ion represented as 12C6 with a +4 charge. Its atomic mass is 12 with 6 protons. Because of the positive charge, it has only 2 electrons, as positive charges indicate a loss of electrons. Atoms can change into ions when they lose or gain electrons. A positively charged ion or cation occurs when there are more protons than electrons. Conversely, a negatively charged ion or anion has extra electrons. This change does not affect the atomic number, which is always equal to the number of protons. Isotopes occur when an atom has the same number of protons but a different number of neutrons. Thus, the atomic number remains constant, while the atomic mass changes, affecting the physical properties but not the chemical properties of the element. Let's explore the types of wave motion. There are 2 main types: compressional waves and transverse waves. Compressional waves move parallel to the direction of the wave. In these waves, compressions are regions where particles are close together, and rarefactions are where particles are far apart. Transverse waves, on the other hand, move perpendicular to the direction of the wave. In transverse waves, crests are the highest points and troughs are the lowest points, and these are equidistant. Now let's look at black body radiation. When objects are heated, they emit radiation. The wavelength distribution of this radiation is dependent on the object's temperature. In general, a red-hot object is cooler than one that appears yellowish. Max Planck, a German physicist, made significant contributions to our understanding of black body radiation. In 1900, he proposed that energy is absorbed or released by atoms in discrete chunks of fixed amounts, laying the groundwork for quantum theory. Emission spectra are the colors of light emitted by an object when it releases energy. Each element produces a unique set of colors, acting like its fingerprint. This unique pattern helps scientists determine what an object is made of. Line spectra consist of special patterns of light made up of colored lines. Each element emits its own set of lines when it releases energy. These lines serve as a diagnostic tool for scientists to identify elements. The quantum mechanical model, also known as the electron cloud model, suggests that electrons don't move in fixed paths like planets. Instead, they move in regions called orbitals around the nucleus. In this model, orbitals are areas where there is a high probability of finding electrons. These orbitals form a cloud-like region centered around the nucleus. The Pauli exclusion principle states that no 2 electrons can occupy the exact same position or perform the exact same action at the same time. This fundamental principle affects how electrons are arranged in atoms. Characteristics of orbitals include energy levels, shape, and orientation in space. Energy levels are represented by positive integers up to 7, defining the orbital's size. Orbitals with the same energy level form an electron shell. The shape of an orbital can take on integral values from 0 to n1 for each energy level n. The values assigned to the shape are given specific letters. Orientation defines the number of orbitals present in a subshell. Electron spin is another characteristic, with electrons spinning either up, which means clockwise, or down, meaning counterclockwise. This spin affects the electron configuration and how electrons are distributed in various orbitals. The electromagnetic spectrum ranges from radio waves to gamma rays and decrease in order of wavelength. This spectrum is crucial in understanding how energy is absorbed and emitted by electrons in various states.